Okay, let's go over 2.3 and 2.4 today. Okay, 2.3, derivatives of natural log. 2.3. Derivatives of natural logs. Okay, derivative of natural logs. Okay, so the derivative of the natural log of x is 1 over x. Okay, that's the derivative of natural log. Okay, if we think of this in terms of the chain rule, okay, ddx of the natural log of u of x, that's going to be 1 over u of x times u prime of x, or u prime of x over u of x. So it's the original function on the bottom and the derivative on the top. So if I have the natural log of okay, so let's look to differentiate some stuff. A. We have y equals 3 natural log of x. What's y prime? Well, that's 3 times 1 over x, which is 3 over x. Okay. So y prime is 3 over x. Okay, b. Okay, y equals x squared natural log x plus 5x. Okay, so we want to find the derivative here. This first part is going to be a product rule. So y prime, derivative of the first times the second plus the derivative plus the first times the derivative of the second. Derivative of the second is 1 over x. Plus the derivative of 5x is just 5. This should be ln x. So y prime is equal to 2x ln x plus x squared divided by x is just x plus 5. That's that one. Okay. C. Okay, y equals natural log of the absolute value of 2x over x cubed. Okay, let's see what happens here. Okay, so we have y equals, this is a quotient rule. So this is derivative of the top. Sorry about that. Come on. Move over. There we go. Okay, derivative of the top. Okay, is going to be 1 over absolute value 2x times the derivative of this absolute value of 2x, okay, is just going to be 2. Okay, this is going to be the absolute value of 2, which is 2. Okay, derivative of that is just 2. Okay. So this is going to be times the bottom. So the bottom is x cubed minus the derivative of the bottom times the top. So the top times the derivative of the bottom, which is 3x squared. All over the bottom squared. That's the quotient rule there. Okay, so what does this become? Well, this becomes 2x cubed, okay, over absolute value of 2x minus 3x squared times the natural log of absolute value of 2x all over x to the 6th. Okay, so okay, I'm going to factor out an x squared here. So x squared. So this becomes 2 over absolute value 2x minus 3. This is 2x, sorry. 2x over absolute value of 2x. Okay, minus 3 times x squared. Or not x squared, minus 3 times natural log of absolute value of 2x all over x to the 6th. So I just factored out the x squared, x to the 6th. So this, 2 of those are going to cancel with 2 of those, maybe with a 4 on the bottom. So 2x over absolute value 2x minus 3 times the natural log of absolute value 2x all over x to the 4th power. Okay, and then, well, this is y prime. Okay, I could go a tiny bit further if I wanted to, but you don't have to. You could stop here. I could say that 2x over 2 times the absolute value of x, because what's the absolute value of 2? Isn't that just 2? And the absolute value of it, the x is the only thing that could be varying. The 2 isn't going to vary. So the absolute value of 2, again, is 2. And so those cancel each other out. Okay, just like we saw back here with the absolute value of 2, okay, equaling 2. Absolute value of 2 is equal to 2 there. Okay, and then that's minus 3 times the natural log of the absolute value of 2x. Okay, all over x to the 4th. Okay. So y prime is equal to this. Those 2's cancel out. I could multiply both top and bottom by absolute value of x to get rid of the fraction. And if I were to do that, I would get x, or so I would get, yeah, x minus 3 times the absolute value of x, multiply the top through by absolute value of x. Okay, times the natural log of that, all over the absolute value of x times x to the 4th. And I could take it there. Okay, so that absolute value kind of messes with things because it doesn't you know, simplify too nicely in the very end. We can't cancel out x's and absolute value x's. It's just not allowed. Okay, number 2. Okay, A. Y equals the natural log of 3x. Okay, this is practicing the chain rule. Okay, so the derivative of natural log of 3x is 1 over whatever's inside here, 1 over 3x, times the derivative of 3x, which is 3. So this becomes 3 over 3x, which is 1 over x, which is kind of interesting. It's kind of interesting property in that if we take just y is equal to, this is y prime by the way, y is equal to the natural log of x, that was 1 over x. So we could actually say that, that this implies that y prime is equal to 1 over x. We could actually say that if y is equal to the natural log of any number times x, that just equals 1 over x. So I should say y prime. Okay, y prime is equal to 1 over x. Okay, so the constants will actually cancel out. Okay. It's kind of interesting. So, oops. Okay, letter B here. Okay, B, y equals natural log of x squared minus 5. Okay, so let's see what the derivative of this thing is going to be. So y prime is equal to 1 over whatever I'm taking the natural log of, okay, times the derivative of x squared minus 5, times the derivative of the inside. That's 2x. So this thing is going to be equal to 2x over x squared minus 5. See? Okay, f of x is equal to natural log of x cubed plus 4 over x. Oh, that's kind of interesting. So this is going to be a natural log, but then it's going to be a quotient rule as well when we do the chain rule here. So it's a natural log, chain rule, quotient rule. Interesting. Okay, so this is going to be f prime of x is going to be 1 over whatever we're taking the natural log of, 1 over x cubed plus 4 over x, okay, times the derivative of the inside, which is a quotient rule. So this is going to be times the derivative of the top, which is 3x squared, times the bottom, which is x, minus the derivative of the bottom, which is 1, times the top, x cubed plus 4, all over the bottom squared. Okay, well, here I'm taking 1 divided by a fraction. 1 divided by a fraction here. And so when I divide by a fraction, it's the same as multiplying by the reciprocal. So this thing just gets flipped upside down. I get multiply by 3x cubed. And then I could distribute the 1, does nothing. I could distribute the negative, and that's just going to change the sign. That's x cubed minus 4. Cool. All over x squared. Okay. So this x and this squared are going to cancel out. Okay. And then the 3x cubed and the x cubed are going to combine. This is 2x cubed. Oops. 2x cubed minus 4 all over x times x cubed plus 4. Okay, and I could stop there if I really wanted to. Say that the f prime of x is equal to this. Okay, if I wanted to factor, I could factor. If I wanted to multiply it out, I could multiply it out. I noticed that one of them, the top is not factored, but the bottom is. You know, it really is personal preference as to which way you want to go here. If you want to leave it in factored form, you can go f prime of x is equal to 2 times x cubed minus 2 all over x times x cubed plus 4. If you want to leave it in non-factored form, okay, or distributed form, you could just leave it like this as well, 2x cubed minus 4 over x to the 4th plus 4x. So either any of these three would be acceptable. Personal preference at that point. But How would I leave it? Well, I would probably leave it like this one. If you were to ask me, I'd probably leave it like this one. Just because visually it's a little bit nicer. You know, you have less symbols, right? You want to simplify things, meaning it has less symbols. So I was able to get rid of the parentheses and the extra numbers here on the outside. So this has less symbols. So I would say that this is the most simplified. Okay, but again, any of these will work. Okay. Okay, number 3. Okay, let R of t equal 80 minus 27 natural log of t, where R of t are the, actually is, I guess, is the retention rate of students after t hours. Okay, so we want to find and interpret, find and interpret, I think that's how it's spelled, interpret, I don't know. Now that I wrote it, it doesn't look right, but whatever. Okay, find and interpret R prime of 2. Okay, find and interpret R prime of 2. Okay, so this is a percentage of information that you would have retained after a certain number of hours. Okay. So let's see what happens here. So R of t is equal to 80 minus 27 natural log 2. R prime of t, okay, is equal to, okay, this is 0 minus, okay, 27 times 1 over t. Okay, so this is equal to negative 27 over t. Okay, so let's see what is R prime of t. Well, this is a rate of change. This is how fast something is changing. So R prime of t is R prime of 2. I'll just put R prime of t is equal to negative 27 over t. Okay, R prime of 2. This is how fast you are losing your mind after, I mean, your memory. Okay, after 2 hours. How fast are you losing your memory after 2 hours? Okay, and this is negative, what's this, negative 13.5. Okay, so this would be negative 13.5% per hour. Okay, so negative 13.5% per hour. And that means that it's going down. It's going down fast. Okay, every hour you're losing, at that point, every hour you're losing another negative 13.5%. Okay, so what does this mean? This means that after 2 hours, the percentage of information retained is decreasing at a rate of 13.5% per hour. Okay. That's the answer when we interpret it. Okay. Okay, let's do a business application. Okay, number 4. I'm done with my business. Busyness. Okay. Busy. Okay, this is a business application. The percentage of the target market that buys a product is a function of the length of advertisement campaign for that product given by f of t is equal to 1 minus e to the negative 0.04 t where t is in days and just t is in days, period. The target market is approximately 1 million people. Is approximately $1 million. No, I'm just kidding. 1 million people. And the price per unit is $1.50 per day. If the campaign K-I-G, right? Yeah. Okay, if the campaign costs $1,000 per day, how long should it run to maximize profit? Okay. Maximize the profit. Okay, so the percentage of the target market that buys a product is a function of the length of the advertising campaign for that product given by this thing here, where T is in days. Okay. So the percentage of the target market that buys a product, okay, is given by how long it's running. Okay. Okay. So let's look at, let's build our profit function. Okay. P of t is equal to R of t minus C of t, right? Okay. So the cost of this thing is going to be, well, it's going to be $1,000 per day, right? That's the cost of running this thing. So that's 1,000 T. Okay. That's the cost function. Okay, but what's the revenue going to be? Well, the revenue depends on what percentage of people buy, right? So what's the percentage of people that are going to buy this thing? Okay. So this is going to be, the revenue is going to be the price times the units, right? Times the number of units sold. The price times the number of units sold. Okay. So that's R of t. And we want it in terms of t, which is the days that this campaign goes out for. Okay. So we're assuming that if we go out longer, that, well, you can't assume anything. Okay, if we go out longer, we advertise longer, we'll make more money. Okay. So let's find out what's the price. The price is $1.50. The number of units that I'm going to be able to sell, well, that's going to be a percentage of, remember this is a percentage, right? This is a percentage. That's going to be a percentage of the $1 million, so of the 1 million people. So the number of units is going to be a percentage of 1 million people minus 1,000 T. Okay, so that's a percentage of 1 million people. Okay, so what is the percentage? Well, that depends on how long the ad runs. Okay, so $1.50 times the percentage function, which is our f of t. Okay, that's going to be 1 minus e to the negative 0.04 t. Okay, times 1 million minus 1,000 t. That's P of t. Okay, so I could clean this up a little bit. Okay, if I were to take this 150 and 1.50 and multiply by 1 million, that's 1,000,005. And then distribute that, okay, to here and to here. I could say that this is going to be 1,000,005 minus 1,000,005 times e to the negative 0.04 t minus, there's a 1,000 t there. Okay, so that's my profit function. My profit function, kind of star that there. Okay, it says if the campaign costs $1,000 per day, how long should it run to maximize the profit? Okay. Okay, so when the profit reaches its maximum, say this function, okay, when the profit reaches its maximum, if I were to go t versus p of t, the maximum value, it'll climb and then it'll peak and then it'll go down, right? So its maximum value will be at the very top of this mountain. The derivative, or p prime of t, at the top of this mountain, the derivative, or the slope of the tangent line here, would be the slope of a horizontal line. And the slope of a horizontal line has slope 0. So the maximum profit will occur when the derivative is equal to 0. Oh, okay. So when the derivative is equal to 0, that's when this function will be maximized, or the days will be the maximum number of days will get me that certain number of days will get me the maximum profit. So, okay, so let's look at P prime of T. Okay, maybe we'll go to, I don't know, go to Desmos and see what this thing looks like. Okay, I'm just curious. What does this thing look like? Okay, it's pretty big numbers, but okay. I'm gonna go y equals 1,500,000 minus, oops, minus 1,000,005.
I think you're missing a 0 on the first.
Oh, thank you.
You're okay.
Okay. I don't even think I need the commas. Let's get rid of the commas. Okay. 1,500,000. Is that a space? Oh. Okay. Times E. Okay, let's go to the keyboard here. Oops. That wasn't what I wanted. I want the keyboard. There. Not that keyboard. Well, this keyboard. There we go. Okay, and then on the functions, there's the exponential function. Okay, that's fine. Exponential function. Okay, that's the same as E, but whatever. Okay, E to the raised to the, okay, raised to the negative 0.04 t, or x in this case, 0.04 for x. Okay, arrow down, and then minus 1,000 x. Okay, so that gives me an arrow. EXP is a function, tries using parentheses. Okay. Oops. What the frick? Okay, I'm just gonna have to type it. Okay, I want y equals 1,500,000 minus 1,500,000 e, okay, e raised to the negative 0.04 x minus 1,000 x. Okay, there we go. Okay, perfect. So now let's see what's happening with this thing. It's going up pretty steep. Okay, so let's zoom out. Zoom out and see what's happening. So, come on, come back to me. There it is. Okay, so yeah, so 3,000, 4,000, 5,000. Okay, so I want to know when's the maximum of this function going to occur. Is it ever going to incur a maximum? Yeah, it does. Okay, so where is the maximum value occurring? It's occurring right there. Look at that. Okay. Honing in on the maximum value here. Okay, so let's see if we can find this maximum value. Okay. It's happening, okay, after approximately 102.35 days. Okay, let's see what happens. Let's see if we can get that. Okay, after 102 days, that's the maximum profit. Okay, maximum profit there. Okay, so looks like 1,372,641. Okay, so let's see. Again, I can't really get a really good picture of this. I mean, it's really stop, behave, stop, behave. I think it's going to get squashed. Squashed. Come on, behave. Yeah, I think the lower I go, the more squashed it becomes. Yeah, I don't think I'm going to be able to get a good squash. Yeah. Well, maybe. Here we go. Stop, be nice. It's not being nice to me. It's not being nice to me. Just be nice to me. Just be nice. Okay, I just be nice. Okay, but you get the idea. There's the peak right there. Boom. Okay, let's see if we can get that. Thank you, Oscar. Okay, so yeah, let's go back here. Okay, let's find the derivative, shall we? Oh yeah. Okay, so p prime of t. Well, what's the derivative of the first value here? It's just, that's it. It's a 0. Okay, this is 0 minus, okay, this is 1,500,000, okay, and then the derivative of e is itself, 0.04t, times the power here, the derivative of the power, that's just negative 0.04. Okay, minus the derivative of 1,000t, which is just 1,000. Okay, so that's the derivative of that. So this is going to be negative times a negative. So what's 1 million times 0.04? Well, that's 60,000. So the negative times a negative here is a positive. So this is 60 grand. E to the negative 0.04t minus 1,000. Okay, and I want to set that equal to 0, and I want to solve. Okay, so we're going to do this. Solve for t. Well, let's add 1,000 to both sides. And we get 60,000. E to the negative 0.04t is equal to 1,000. Okay. Divide by 60,000. Okay. And I get e to the negative 0.04t is equal to 1 over 60. Okay, so, oops. Oi. Okay. Now, how am I going to solve for t? Well, t is the exponent, so I'm going to take the natural log of both sides. And I'm going to bring this down now. 0.04, negative 0.04t is equal to the natural log of 1 over 60. And so let's divide by negative 0.04t. Negative 0.04. Oh no, just the negative 0.04, because we're solving for t. Okay, so we want natural log 1 over 60. Okay, natural log of 1 over 60. So let's do that. Let's do 1 divided by 60. Let's take the natural log of it. Boom. And let's divide by negative 0.04. 0.04 negative. And I get 102.35. Okay, 0.358 or 102.36, exactly the same thing that the graph got. That's kind of cool. 102.36, sorry, no, 36. Okay, or roughly 102 days. Okay, 102 days. So the ad campaign, okay, should run between 102 and 103 days, okay, in order to maximize the profits. Okay, so the ad campaign should run, okay, it will maximize profits. It won't maximize the profits on the 102nd day. Okay, it will maximize the profits somewhere on the 103rd day, right? Because if you only go to 102, you still haven't hit your maximum. Okay, but on the 103rd day, it will hit the maximum at some point. And so I would say the ad campaign should run 103 days, just to make sure I hit that maximum value. Okay, to maximize profits. Okay, but what you could actually do is you actually could calculate that. You could say, well, what was P of 102 and what's P of 103? And then you would just calculate it out and get the maximum value, okay, of those two. Because you can't just say, oh yeah, I'm gonna run the ad for, you know, 102.36. Maybe you could. Maybe you could just say, hey, I'd only want to run it for 8 hours. So you could say, oh, I want to run it for 102 days, 8 hours, because that's about a third of a day, right? 8 hours. So you say, hey, after the first 8 hours of the day, cut the ad. So, but if you could only do it in whole days, then you'd actually want to plug it into your original function, okay, and then calculate that out. I wonder if we could do that real quick with this thing, okay. If will it move at all? Nope. I don't think so. Let me see. Will it calculate the 102nd day for me? So 102nd day. Okay, the profit on the 102nd day is, oh, it did. Oh, shoot, I was so close. There. Oh my gosh, I breathe and it moves. Let me take a deep breath and hold my breath. Nope, I can't do it. Why can't I do it? Because I can't hold my breath and teach at the same time.
Can you type in a value for X?
Can I? Can I do that? I don't know. I don't think so. Oh, maybe I can. You're right. Oh, yes. So X equals 102. And then I can find the intersection of that. Sweet. Thank you so much. Perfect. Hey, you helped me not have to hold my breath.
Cool.
Okay, let's also do 103. And let's compare the two. Boom. Okay, and we'll see which one is higher here. Which one is higher? Is that one higher? 1,372,638.80. Is that one higher, or is 103 higher? And I would say that 102 is higher. So 102 beats out 103. Okay, but the maximum is right there. Okay, that's the max. So I would go with 102 days actually to maximize if I had to chunk it into days. So 102 is equal to C Desmos. C Desmos. But 102 is your max. Okay, so I would say 102. Okay, okay, let's go to 2.4. Okay, is exponential and logistic growth. Okay, exponential and logistic growth. And logistic growth. Okay, so if we have y equals CE to the kx, this is the exponential growth function. Okay, that's the x. If I take the derivative y prime, this is CE to the kx times k, okay, by the chain rule. I could say this is y prime is equal to the original function times k, y times k, or I'll write this as ky. Okay, the original function is y, and then I just multiply that by k. And so this is called a differential equation, or derivative equation. Differential is just a fancy word for derivative. So this is a derivative equation or a differential equation. Okay, why? Because it has a derivative in it. So if you have y prime equals k times y, this equation implies exponential growth. This is your exponential function. Okay, the other way of writing this is that if we have y prime over y equals a constant, well, that's still exponential growth. Okay. Okay, for population growth, the exponential growth model looks like this. It's like the PERT account that I think I explained already. P e to the RT, that's for population growth, where this is your initial population. This is your final population. Okay, the rate is the growth rate, R, and T is the time. Okay. For finance, your exponential growth is A equals P e to the RT. That's the PERT account. Okay, your PERT account. Okay, where P is the principal, A is equal to, okay, the final amount. Okay, this is your, what we call your present value. This is your future value. Okay, and rate and time are the same. Okay. Okay, let's look at number 2 here. Or sorry, number 1. I didn't even do number 1 yet. Okay, number 1. Okay, we want interest compounded continuously. Okay, interest compounded continuously. Suppose that P dollars is invested at a rate of 7% such that dA dt is equal to 0.07a. I'm like, okay, what the heck is going on here? Okay, so this dA dt, that's a prime. I know what that is. That's a prime of t. Okay, dA dt is a prime of t, which is equal to 0.07a. Okay. Well, remember when we had the derivative a prime of t over a, if I divide by a, is equal to 0.07. Oh, look at that. That's k, right? That's k. Remember this, when I had this scenario, right? When I had y prime over y equals k, what was that? Well, that meant that y had to be equal to ce to the kx, right? So kx. Okay, in this case, we just have to figure out, well, what are we dealing with? Well, we're dealing with a instead of y, so that's a. A is equal to kc. Okay, we'll get to what c is in a second. Okay, so this is c. Okay, e to the k, which is 0.07 times x. But this y of x is, y is usually a function of x, right? Y is equal to some function of x. We could say that y is equal to f of x, right? So we could actually change this y prime into an f of x. And it's f prime of x over f of x is equal to k. Oh, okay. So that means that this y I could write as a f of x as well. F of x, okay. So this is going to be a of t, right? A of t, because it was a prime of t, which means what's the variable here? The variable is not x. It's no longer is it x. It is t. So this goes to a t. Okay. So if it's compounded continuous, this is a is equal to c e to the 0.07t. But we know what c is when things are compounded continuously. It's not c, it's p. Oh, look at that. That's my PERT account right there at 7% interest. Oh, okay. So at 7% interest, that's my PERT account. So if it had this function here, then I could go directly here. Okay, you don't have to do this process. You just say, hey, you know what? Once I have this set up, I know that this is equal to that. Oh, okay. And so let's answer this question. If $100 is invested for 1 year, what is the future value? Okay, what's the future value here? Okay, so A is equal to, I'm going to invest $100 E to the 0.07 times T, which is 1. Okay, so this is going to be 100 E to the 0.07, which is going to be approximately what? Go to the calculator. Okay, clear. Okay, so the calculator is going to show 100 times E raised to the 0.07 power, boom, is equal to $107.25. I would have made $7.25 in interest. Okay, over that first year. Okay. Okay, how long to double the amount. We'll call this A, we'll call this B. Okay, how long to double the amount? Oh, okay, well remember, I know what my doubling time is equal to the natural log of 2 over R. Oh, okay. So what's the doubling time? Well, the doubling time is going to be the natural log of 2 over the rate. What's the rate? 0.07. So this is going to be equal to, I'm going to have to go 2 natural log, well, that's 0.693. And then I'm going to divide that by 0.07. And I get about 9.9 years. Okay, well, I'm going to say this is about 10 years. Okay, does that make sense? That would be about 10 years. Yeah, let's look at the rule of 72. What's 72 divided by 7? Well, 72 divided by 7, that's about 10 years. Right, isn't 70 divided by 7 10? So yeah, it's about 10 years. Okay. Okay, so keep that in mind for our doubling time. Did we go over this already? I feel like we already went over that doubling time. So hopefully we did. I think we've gone over it a couple of times. Okay, let's finish today by talking about the Marvel movies. Okay, is anybody here a Marvel fan? Okay, Marvel fans unite. Okay, I'm also a DC fan, so I'm a closet DC fan. Okay, I don't tell a lot of people I'm a DC fan, but I am as well. Okay.
I like
Define Marvel, MCU. Okay, I'm defining Marvel as MCU. Okay, and I'm defining DC so far as DC EU, which it's the DC extended universe, which is kind of weird. So it's kind of like DC does not acknowledge its movies because it's in the extended universe. It's not canon, but Marvel does just because they want the ching ching, I guess, the bling bling, ching ching. Okay, so who knows? It's all political anyway. It's all to get my dollars. Okay, it's just all about the dollars. Okay, so I'm sure most of you have seen something called Endgame. Okay, yeah. I mean, I think it's on every streaming service at this point. Okay. Okay. So we're going to talk about the Marvel at Endgame, right? So, or even Infinity War. Okay, let's talk about Thanos here. Thanos was an idiot. He did not know his math. Okay, he needed to go back to school. He needed to take business calc. Had he taken business calc, he wouldn't have made such a tragic error in his understanding. Okay, so there is something called logistic growth, population growth. Okay. Okay. That was funny. Okay, so logistic population growth. Okay, logistic population growth. Logistic population growth has a maximum. Thanos got that right. Way to go, Thanos. There is something called a carrying capacity in a closed system. Whether that system be a planet or universe or whatever, it has a closed in any closed system, there is something called carrying capacity. And so to prevent overpopulation, Thanos snapped everyone in half. No, not like literally everybody, but the population of everybody in half. Okay, so the problem with this is that populations that have a carrying capacity or a maximum here, which we'll call L. L is this for limit, right? We're learning about limits. Look at that. So as t goes to infinity, the limit goes to L. Make sense? So what's L? L is the carrying capacity. Okay, before disease and famine takes over, you know, and kills everybody anyway. Okay, so okay, we've always had something like that happen. They're called plagues. They don't call them, you know, they didn't have nice terms like COVID and everything, you know, 1,000 years ago. They call them plagues. Okay, so COVID-19 plague, right? So that was the old school term. Okay, the black plague. Okay, it's killing everybody. Okay, they didn't have nice terms like the Spanish flu. Didn't that sound so nice? Spanish flu. Just happened to kill tons and tons of people. Okay, so the problem with Thanos's theory here is that what? Is that up until, we'll call this L over 2, up until L over 2, this logistic population growth function behaves exactly like an exponential growth. This is exponential growth. But as soon as you hit L over 2, which is half the population, right? Which is half the population. The universe is not finite. Have you read anything about Stephen Hawking? It's an expanding universe, but it is a finite universe. So, yeah, wrap your head around that one. Einstein proved that over 100 years ago. Finite universe. Okay, so and time is a relative construct. Figure that one out too. That'll mess with your mind at night. Late at night, 3 o'clock in the morning, trying to figure out, okay, if I go through a black hole, time changes. So yeah, that'll mess with you too. So, yeah. Okay, so exponential growth, right? Up until we hit the half of the carrying capacity. So what's the problem? The problem is once you add one more person after half, this starts happening again. We start getting overcrowding. So so he was an idiot because he just snapped half and retained the same freaking problem. Does that make sense? Like, as soon as you're half, you start pushing that envelope again, and your curve starts going like that. So go back to school, Thanos. It doesn't work. I mean, if you really want to do it, maybe you should have cut it into like L over 8, just like right here. Okay? But to do L over 2, bad premise. Bad premise. Okay? Why am I bringing this up? I don't know. I'm a Marvel fan. No, I'm just kidding. It's because we need to talk about this. This is logistic growth model. Okay? The population growth that has a limiting value. Yeah, exactly. He is. Sort of. They steal from each other. Okay? They just steal back and forth. Okay? There's so much stealing in those two universes, it's crazy. Okay? Just steal, steal, steal. Okay? So I'm like, oh, I read this one comic. Okay, I'm going to make a clone of him over here. And it's like, whatever. Okay, that's okay. Okay, the population growth that has a limiting value. A limiting value is modeled by P of t equals L over 1 plus C e to the negative kt. Oh, look at that. That's my exponential growth that has a limiting value. Actually, 1 plus the exponential decay model, but we're inverting it, so it's growing, but then it has a limiting value. You can only get to L. You can't get past L. L is the boundary. Okay. K is the growth rate. This is the growth rate. And T is time, obviously. Okay. And C is our initial amount. Okay. It's our initial population. Okay. We want to find for our last, I don't even know what number we're on anymore. We're on number something. I lost my numbering. Number 2? I guess we're on number 2. Okay, number 2. Okay, so find the rate of change. And this could be a population of money. This could be a population of bacteria. This could be a population of whatever. Okay, find the rate of change at which phone subscriptions are growing if the number of subs is modeled by is modeled by n of t is equal to 24 over 1 plus 34 e to the negative 0.6 t. Okay. If n is in millions of subs, okay, and t is the number of years after 2000. Okay, so we want to find out basically how fast our subscriptions growing, how fast we'll say were. Now let's just do are. How fast are subscriptions growing in 2020? Boom. Let's bring it up to date. Okay. How fast are they growing in 2020? Okay, so we want to find out the rate at which this thing is moving. That's a derivative. Thing is derivative. So we're going to have to take the derivative of this thing. Okay, it's not that bad. Okay. So n prime of t, let's look at what n of t is. Well, I'm going to rewrite n of t just to make it a little simpler. Okay, I don't want to do a quotient rule if I don't have to. Okay, so I'm going to say n of t is equal to 24 times 1 plus 34 e to the negative 0.6, that's a 6. Okay, negative 0.6 t to the negative first power. Okay, I turned it into an exponent instead of a quotient because exponents are a little easier to deal with. Okay, this is still a chain rule though, but it's just a little nicer this way. Okay, I didn't want to do a quotient rule if I didn't have to. So let's do n prime of t here. This is 24 times the derivative of the outside. What's the derivative of the outside? It's negative 1 times 1 plus 34 e to the negative 0.6t to the negative 2, okay, times the derivative of the inside, which is 0 plus 34e to the negative 0.6t times this e to the negative 0.6t. If I take the derivative of that, it's itself times negative 0.6, okay, the derivative of the exponent. Okay, let's try to bring this all together. This is a negative 1. Okay, so this is n prime of t is equal to, okay, I've got a bunch of stuff here. I've got a 24 times the negative 1, that's negative 24. I've got a 34. Well, let me not skip too many steps here. Okay, so I'm just going to go negative 24 times 1 plus 34 e to the negative 0.6t to the negative second power, okay, times 34 times negative 0.6. So what is that? What's 34 times negative 0.6? 34 times 0.6 is 20.4, okay. So this is negative 20.4 e to the negative 0.6t. Boom, okay, nice. Okay, so I'm going to now multiply these two together. Okay, the negative and the negative will cancel out. So n prime of t is equal to 20 times 20.4, 24 times 20.4 times 24 is 489.6. So 489.6 e to negative 0.6t on top. This whole thing here will drop down below because it's a negative exponent. 1 plus 34 e to the negative 0.6t squared. Okay, that's cool. Okay. And we want to know, well, what are the subs in 2020? Well, t is number of years after 2000, so n prime of 20 is going to be 489.6 e to the negative 0.6 times 20 all over 1 plus 34 e to the negative 0.6 times 20 squared. Okay, so we clean this up a little bit before I try to plug it in the calculator. 489.6 e to the 0.6 times 20, that's 12. This is negative 12. All over, okay, all over 1 plus 34 e to the negative 12 squared. Now I'm going to plug it into the calculator. Okay. I might have to do it separately, but it's all good. Okay, so 489.6 times e raised to the negative 12th power is 0.00003. So 0.00003. Oh, this is going to be a pain. 0.003 008. Okay. 008. Okay. I'll just go out 6 decimals. Okay, divided by the bottom here squared. Let's try to plug that into the calculator and find out what that is. Okay, let me just make sure I did that correctly first again. So I have e raised to the negative 12th power. Boom, is that, okay, times 489.6. Boom, okay, perfect. Okay, let's do the bottom. The bottom is 1 plus 34 times e raised to the negative 12th power, to the negative 12th power. I'm going to close the parentheses, and then I'm going to square this. Squared. Boom. Okay, so this is going to be 1 point, it's practically 1.0004, 417, okay, 417. I'll do 418. 418. Okay, let's divide the two numbers. Okay, 0.003 008 divided by 1.000418, okay, is, yeah, I figured it would be pretty similar, is 0.0030067. 0.0030067. 0.0030067. Okay. Now, it looks like a really small number, except for the fact that what is n in? N is in millions. Okay, so what I can do is I can now multiply this times a million. So this is 0.00030067 times a million. Okay, so times 1,000,000, okay, is 3,000. Okay, that's 3,000. Okay, 6.74. Okay, 6.74. So roughly, I'll just do 0.7. So roughly 3,007, okay, new subs per year. Okay, it's pretty low. Okay, but that's the deal there. Okay, so 3,007 new subscribers per year. Okay, that's how fast they were growing. Now, why are they not growing so fast? Why is it only growing by 3,000 when we're talking about millions? Because this is what's happening. As we start here, okay, and our limiting value is this 24 million, okay, 24 million that was on top, and we start at 1, and we go up, and then we peter out. So the rate of change gets, the amount that I go up every year gets smaller and smaller and smaller. That's the rate at which I'm growing. Every year gets smaller and smaller. And so, you know, down here, you've got a huge growth rate. But up here, after this might be after year, say 5, after year 10, and then way out here after year 20, boom, you're not growing much. You're only growing by 3,000 new subs per year. Okay? So maybe that certain cell phone carrier is working, you know, not doing so well. Okay, it had a growth capacity of 24 million subscribers. Once it hit that growth capacity, it couldn't grow anymore. Okay, or it was growing, but it was growing very slowly. Okay, that's all I got for today.